Hey fellas, welcome back to the channel. In today's video, you're going to go through the design of a cantilever retaining wall step by step. We're going to look at soil pressure, design of the wall for bending, do the stability checks like overturning, sliding, and bearing check. We're going to design the footing for bending, and we're going to also look at the reinforcement detailing. So let's get into it. So we're going to go through exercise number 1 of my concrete block retaining wall ebook, which is the type 1 of this page, and it has the soil on top of the footing. So if you're interested in learning more about retaining walls, I'll leave a link in the description below where you can have access to this ebook. Not only will you learn about retaining walls, but I also go through the design of concrete and masonry elements in shear and bending, and there's a lot of information about the design of footings and reinforcement detailing as well. So check that out in the link in the description below. So pretty much we're going to go through this exercise here, and the way this question is worded is that an engineer had a meeting with a client and they decided to go for a concrete block retaining wall. So the wall will be located at the boundary of the property, and since the client's land is on the high side, the footing will have to be installed entirely within his property. Okay, so you've got the boundary here, and obviously you cannot build any structure outside of the boundary. You don't want to build part of your house in your neighbor's property. Now we've got the soil parameters here. The wall height is 3 meters. Unit weight of the soil is 18 kilonewtons per cubic meters. We're dealing with sand. It has the angle of friction, internal angle of friction of 30 degrees. Sand is cohesionless, so we're dealing with a cohesion equals to 0. Ka, which is the active earth pressure coefficient, is 0.377. We're going to discuss this in the next slide. I'm going to show you how we got this number. Q equal to 5 kPa, that's the surcharge. Then we've got our first tip here, which is refer to table D4 of AS 4678 for usual soil classification. So AS 4678 is the Australian standard for earth retaining structures. You check table D4, you're going to see some usual soil classifications. Now we do have some soil reduction factors. You can refer to table 5.1a of AS 4678. So we pretty much need to factor the internal angle of friction in 85%. So instead of using 30 degrees, we're going to use 25.5, and the cohesion we're gonna have to use 70% of the cohesion. Obviously, since our C is 0, 0.7 of 0 is 0. But if you had cohesion, if you're dealing with a soil with cohesion, you would only use 70% of that cohesion. And then here we've got the wall soil friction or wall friction. It is a common estimate for this parameter using 2/3 of the internal angle of friction. You might want to research and see if you need to use another value for your specific scenario. Earth pressure theory. We're gonna use the active pressure as we're dealing with a cantilever retaining wall. This is a cantilever retaining wall. It will move, it will deflect a little bit. That's why we're gonna use the active pressure coefficient. If your wall is not gonna move, or if you have a different type of wall, you might have to use different K. And we are going to use the Coulomb method to find out the active coefficient Ka as per the table below. So another tip here, refer to table E1 of AS 4678 for application of each earth pressure theory. So you might decide to use Rankine instead of Coulomb. You can also use Rankine. You just need to do a research into what your scenario is. Make sure you understand what each earth pressure theory accounts for. For example, the Rankine doesn't use cohesion of the soil, and consider a smooth wall. So for every type of for each scenario you might use different types of earth pressure theories. We're just gonna go with the Coulomb method in this one here. So the Coulomb active earth pressure, since I'm a very nice guy, I already put together a table with diverse values of Ka for different internal angle of frictions, different wall frictions, alpha and beta angles as well. So beta is just the slope of the soil behind the wall, and alpha is pretty much the inclination of the wall. If we go to the table here, 25.5 and 2/3 of 30, which we calculated previously, is 20. So we get the Ka 0.377. If you have another values that do not show in this table, you can use this equation here. All right, next slide. What we're gonna do now is we're gonna draw the free body diagram and find the soil and surcharge loads. So we're gonna design a stick here, right? And this stick is, just imagine a vertical beam, a cantilever vertical beam. So the free body diagram is just a stick fixed at the base, and this stick here has 1 meter of length into the page. Okay, so imagine that all the calculations that we're gonna do is for a 1 meter long wall. Okay, so it's 1 meter going into the page, and we've got a rectangular load distribution for the surcharge, and this rectangular load distribution we've got here at the base a pressure of Q times Ka, which is the 5 kPa times 0.377, that's equal to 1.885. And if we look at the triangular load distribution here for the soil, it is gamma H Ka, which is 18 times 3 times 0.377, that's equals to 20.36. So that's the unit weight of the soil times the depth of the soil, or the wall height, times the earth pressure coefficient. Now, I don't know if you remember your hydraulic classes and you had to calculate the water pressure or hydrostatic pressure. You would do the unit weight of the water times the depth of the water. So it's pretty much what we're doing here. You know, it's the unit weight of the soil times the depth of the soil, but here you also include the earth pressure coefficient. We've got another tip here, which is the actual pressure forces act on an inclined plane, and we are simplifying this problem. So in reality, I'm gonna try to draft this here. It's gonna be a bit of a mess, but in reality, this rectangle is this, and then the triangle is like this, and then the forces act like this. And then what you need to do is you need to decompose this force in X, and then decompose this in Y, and then you have the forces acting on the wall. We're pretty much disregarding this and just using everything as an X horizontal direction. So I'm just going to delete this here so it doesn't mess up this slide. Okay, cool. So simplifying this load distribution here, you've got a trapezoidal load distribution that we broke this down into a rectangle and a triangle, and now we're breaking this down into a point load. Okay, so F1 is the point load for the rectangle, and F2 is the point load for the triangle. And as you might know, I hope you know that. If you don't know, that's fine. These forces act at the centroid of these figures. Okay, so the centroid of the rectangle is going to be half of the height. That's why F1 is acting at half of the height, and then the centroid of this orthogonal, right angle triangle, or orthogonal triangle, whatever you want to call this, rectangle triangle, is at 1/3 of the height of the triangle from the base. So F2, which is for this triangle, is acting at 1/3 here. So the loads from the soil and surcharge are the area of the triangle. So F1 and F2 are the area of the rectangle and triangle respectively, and they act at 1/3 and 1/2 from the base. That's what we just explained here. So let's calculate the area of the rectangle, which is just simply base times height. So the base is 1.885 and the height is 3 meters. So that works out to be 5.655 kilonewtons per meter of wall. So that's per 1 meter of wall into the page. Now the area of the triangle is base times height divided by 2. So the base is 20.36 times the height of 3 divided by 2, and that gives us 30.54 kilonewtons per meter of wall. Now we do need to factor these loads, okay? So we're going to use the load combination of 1.2 G plus 1.5 Q. G is the soil loads, okay, so that's the dead load, and Q is the live load, which is the surcharge. So we're gonna use 1.2 for the dead load and 1.5 for the live load. 1.2 times 30.54 and 1.5 times 5.655. Now that's exactly what we've got here. Same free body diagram, but now with the factored point loads acting at 1 meter and 1.5. 1.5 is 1/3 of 3. 1 meter is 1/3 of 3. 1.5 is half of 3. With these point loads, we can draw the bending moment diagram, which would look like something like this for point loads. We can also simply draw the bending moment diagram for this trapezoidal load distribution. It's just that if we do it point loads, makes things simpler, and we can just calculate this bending moment diagram by the summation of the bending moments from these point loads. So if we have a look at the surcharge, we've got 8.48. The lever arm is 1.5. So the bending moment is force times distance, 8.48 times 1.5, we've got 12.72. Same procedure for soil. Soil is 36.65. Lever arm is a meter. Force times distance is equal to 36.65. And now we just need to add up these numbers, and that's how we get to 49.37 kilonewtons meter. And that makes way easier than actually drawing the free body diagram for the trapezoidal load distribution. However, you might want to draw this bending moment diagram for a trapezoidal load distribution, because I'm going to explain you in the next slide that you don't want to use the same reinforcement throughout the whole wall because it's not economical. So you might want to know what's the bending moment of the wall at this point here, for example, you know, up in the wall. And this is the bending moment diagram for the actual load distribution. And we're going to talk about that in the next slide. So the bending moment for walls over 2 meters high is usually too large to use only 200 series blocks. So the 200 series block, they are masonry blocks of 190 millimeters. And what I'm saying here is that if you have a wall that is, let's say, 2.2 meters or 2.4, anything over 2 meters high, you want to use a thicker block, you know, a wider block. And that's what I'm saying here. So for this reason, we will utilize 300 series block, which are 290 wide up to 1 meter of wall height, as per the image below. I'm going to show this image in the next slide, and you can understand what I'm saying here, okay? So pretty much the next step is to find the bending moment capacity for a 290 block, which is the 300 series. And I'm assuming here, okay, well, this is just an assumption, that we're gonna need N16 at 200 centers, okay? I assumed 16 diameter bars and 200 centers. Why did I assume 200 centers? So if I use 200 centers, that means the builder will install reinforcement in every core of the block. So I'm just assuming that he's gonna install reinforcement in every core here. Those are the parameters, the dimensions of the masonry block that we're gonna use. So the dimension L is 390, which is this length here. Dimension T is 290. The height of the block is 190 millimeters. The height here is actually into the page because we're looking at a plan, the block. And the mortar bed joint thickness is 10 millimeters. The mortar is just that paste that we connect the block masonry together. And the steel reinforcement, okay, N16 at 200 will give us a 1005 millimeters squared area of steel. Cover, we're using 55 millimeters. The yield strength of the steel is 500 MPa, and the effective depth is 290, which is T, minus cover, minus half of the diameter of the bar, and we get that the effective depth is 227 millimeters. Now moving to the masonry parameters, you can have a look at AS 3700 2018 tables 3.1 and 3.2. I would suggest you going to this standard and having a look at what these terms mean. If you don't know, if you're not familiar with these numbers, I'll quickly just run you through here. So FUC is the characteristic unconfined compressive strength of unit, and that's equal to 15 MPa. Km is the compressive strength factor, and you're gonna get on these tables here, it's equal to 1.6. KH is the joint thickness factor, 1.3. FMB is the characteristic compressive strength, which is equal to 6.2 MPa. And the design characteristic compressive strength is Fm, which is equal to this formula here, and that works out to be 8.06. You're gonna find everything in this standard, and it's just a matter of following these numbers here. Okay, so now this is the detailing of the wall. As I mentioned in the previous slide, we've got 1 meter high of 300 series blocks. So these blocks here, they are 290 thick, and the rest of the remaining 2 meters of wall will be just a 200 series, which is 190 thick. So what we're doing here, we're using N16 at 200 for the wall, which is this reinforcement here. We're gonna lap this N16 at 200. We're gonna lap 700 millimeters with N12s at 400, okay, because we're not gonna use N16 at 200 all the height of the wall, because that's not economical. So we can use a smaller bar up here where the bending moment is smaller. That's why I mentioned previously in the slide before that we want to know what's the bending moment from here up to here, so that we can check that N12 at 400 works. And how you do that, you pretty much do the same check that we're gonna do in the next slide for the N16 at 200. The starter bars, I'm just matching these starter bars with the reinforcement of the wall. And now let's make sure, let's see how I got N16 at 200 centers to work. But before, let's just have a look at this tip here. Bending moment is maximum at the bottom of the wall, and it reduces at the top of the wall. So it's not economical to use the same steel higher up in the wall where the moment is less. So what we're gonna do, we're gonna perform another design and ensure that N12 at 400 centers at the top works. So you're gonna have to see the trapezoidal load distribution bending moment diagram. So moving on, we're gonna design now. We're gonna check that N16 at 200 centers work. And how we do that, firstly, we need to know the area of steel that we're gonna use. And the area of steel for the calculation of the bending moment capacity is the minimum of 0.29 times 1.3 times Fm times B times D divided by Fsy, or the area of steel that we have. So if we substitute all the numbers into this formula here, so using B, so B is 1 meter, okay, so it's 1 meter length of wall into the page. I'm just changing that to millimeters. We get that the minimum of these two numbers here is 1005, which is the area of reinforcement of N16 at 200 centers. Now, if this formula here would give you a number smaller than 1005, you would have to use that number, because it's the minimum that we're using. The bending moment capacity is phi Fsy ASDD times 1 minus 0.6 times Fsy ASD divided by 1.3 Fm times BD, and you can also find that in AS 3700 in the clause of the bending moment calculation. If we substitute all these terms by the numbers, we will get that our bending capacity is 74.7, which is greater than 49.37 kilonewtons meter. Therefore, we are okay. So N16 at 200 works. So we're good with that. We're just gonna run with these numbers, with this reinforcement. Now the next thing we're gonna do is the stability check. we're going to check overturning of this wall. So what we need to know the self-weight of the 300 series blocks. We need to know the self-weight of the 200 series block. We need to know the self-weight of the soil on top of the footing. And we need to know the self-weight of the footing itself. The self-weight of the 300 series block is the thickness of that block, which is 290 millimeters, 0.29 meters, times 1 meter of height of block, times 1 meter long wall, times 24, which is the unit weight of the concrete block. That gives us 6.96 kilonewtons. Now the 200 series blocks, they are 190 millimeters thick, which is 0.19 meters, times 2 meters high, because we've got a 3 meters high wall. So if 1 meter is the 300 series, the remaining height is 2 meters. So we're going to use 2 meters times 1 meter long wall. Remember, 1 meter into the page times the unit weight of the concrete block. That gives us 9.12. So the total self-weight of the wall is the summation of these both numbers, and it is 16 kilonewtons. Now the self-weight of the footing is 300 thick, 300 millimeters thick, that's 0.3 meters, times 2.4, I've got a 2.4 long footing, times 1 meter long wall, so it's 1 meter of footing into the page, times the unit weight of the concrete, we're just using 24 as well, that gives us 17.28. And now the self-weight of the soil, okay, so the self-weight of the soil is pretty much all the soil that we have on top of this footing here, and that is 2.4, which is the length of the footing, minus the thickness of this block, times the whole height of the wall, times 1 meter of length of wall, right? So that's 1 meter of soil into the page, times the unit weight of the soil, which is 18. That gives us 113.94. And we've got another tip here. So the surcharge is not always present. We're going to disregard this load, as we cannot rely on it to help counteract overturning. So pretty much we have a surcharge here, but we're not going to use that to help us to prevent overturning, because we know that surcharge might not be always there. So we don't want to rely on that force here on our calculations. Now what we're going to do, we're going to take the moments about this point O here. See this red point O here? So we're going to take the moments about this point and make sure the resisting moments are greater than the overturning moments. Otherwise our wall will overturn, and we don't want that to happen. So moving on to the next slide, we're going to take moments about O. So the overturning moments M0. I'm just going to bring this image here so we can have a look at what we're doing. So M0 is 8.48 times 3 divided by 2, which is where this load act on. You remember, half of the wall, plus 0.3, which is the thickness of the footing, plus 36.65, that's the load of the soil, times 1/3 of the height. Again, that's the point where this load is acting, plus 0.3, which is the thickness of the footing again, and that gives us 62.9 kilonewtons meters. Now the restoring moments MR, we're gonna use the self-weight of the soil times 2.4 minus 0.19, which is the thickness of the wall here. I'm just disregarding that we have different thicknesses. Okay, so I'm just using 0.19. We're going to divide that by 2. So dividing that by 2, it's the distance from here up to here. And then we add 0.19. That's going to give us the distance up to the point O. Okay, so repeating that again. So it's 2.4 minus 0.19 divided by 2. That's the distance from here to here, plus 0.19. Okay, so we're pretty much trying to find the distance from this point load here horizontally, okay, the perpendicular distance horizontally up to the point O. Okay, and then that distance is 1.295. Then we just multiply the self-weight of the soil that we found in the previous slide, which is 113.94. That gives us a restoring moment of 147.55 kilonewtons meters. Okay, so now we are gonna find the self-weight of the footing and the restoring moment for the footing. Just gonna bring that image back again. So the footing, WF here, that's the self-weight of the footing we found before, which is 17.28, and we're just gonna multiply that by the distance of the centroid of this footing, which is a rectangle, the distance from the centroid here to the point O. So that's very simple. Okay, so that's 2.4 divided by 2, and then we get that 17.28 times 1.2 is equal to 20.74 kilonewtons meters. Now we know the restoring moments, the resisting moments, and we know the moments that are trying to overturn this wall. So what we're gonna do, we're just gonna compare them and see which one is larger. Okay, but before we do that, we want to factor our restoring moments, and we do that by factoring that number by 80%. Okay, so we're gonna multiply MR by 0.8. So 0.8 times 147.55 plus 20.74, that needs to be greater than 62.9, and we can see that these numbers is way larger than the overturning moment. So we're happy, therefore okay, we're happy with that. The wall is not gonna overturn. So our next tip here, usually overturning will not govern if soil on top of the footing. What that means if you have a wall that the footing goes under the soil and you're getting that this wall is overturning, you might be doing something wrong in your calculations. Now the next stability check that we're gonna do is for sliding. We do need to know the coefficient of friction, and you can find this in this link here. Obviously you can't click on this link, right? But anyway, you can just do a search online and you're gonna find coefficient of frictions for different types of soil. Here we're gonna adopt a coefficient of friction of 0.5, and the sliding resistance is the self-weight of our structure times the coefficient of friction, and that is the self-weight of the wall plus the self-weight of the footing plus the self-weight of the soil times 0.5. That's going to give us a resistance to sliding of 73.61 kilonewtons. Again, we're going to also factor this number by 80%, so 0.8 times 73.61. So we've got a sliding resistance of 58.89 kilonewtons. So as long as the sliding force, which is the sum of the surcharge plus the soil load, 45.13, so as long as the sliding resistance is greater than the sliding force, our wall obviously is not gonna slide. So 58.89 is greater than 45.13, therefore okay. So again, we've got another tip here. If the subgrade soil is cohesive, so if you have a silt or a clay, adhesion between the bottom of the footing and soil should be considered in lieu of friction. So instead of using the coefficient of friction, you're gonna use a adhesion number. Now, the passive earth pressure of the soil in front of the footing may also be used to stop sliding. So if you are absolutely sure that no one's gonna excavate in front of the footing, and you will always have the soil in front of that footing, you might use that soil to prevent the wall from sliding. I personally wouldn't recommend using that. I would just disregard that soil because, you know, it might not be very well compacted. We never know what's happening there, so just be conservative and disregard the soil. So let's moving on. We're gonna check the bearing. Okay, so let's do a bearing check. So what's happening here is that we've got all these forces applied to a wall, and we gotta make sure that all these forces are transferred to the soil, and the soil has enough bearing capacity to resist these forces. So let's have a look at the pressure distribution under the footing. What's gonna happen here is you've got these forces trying to push the wall here. And logically, if you think what's happening here, the pressure on this area here will be greater than the pressure on this area of the footing, right? That's why we've got a distribution of pressure like this one. We've got P max where the point O is, and then we've got P minimum right across where in the other side of the footing. So all these vertical forces here on the wall, they will be equal to a V force under the footing. Action reaction, we've got V here, and that needs to be equal to the self-weight of the wall plus the self-weight of the footing plus the self-weight of the soil plus the surcharge. So we found these numbers before. So self-weight of the wall is 16, self-weight of the footing 17.28, and the self-weight of the soil 113.94, and the surcharge is 5 kPa times 2.4 minus 19 times 1 meter length of wall. Okay, so we are pretty much accounting for a surcharge that is the same area of the soil above the footing. That's going to give us 147.22 kilonewtons, and then we're going to have to find this distance x here, which is the distance of the V force to the point O, and this distance is equal to the m net divided by V. Okay, so m net is the moment equals force times distance, so m equals to V times x, so x equals to m divided by V. And what is m net? M net is the resisting moments minus the overturning moments. Now the resisting moments we calculated before at the overturning check. So if you remember, just go back a couple of slides, and you're going to see that our resisting moment is 168.29 kilonewtons meters, and the bearing capacity check is carried out using service loads, therefore adopt G. Okay, cool. So for the bearing check, we're not going to use the ultimate loads, we're going to use the service loads. Okay, so always for deflection and also bearing check, you use the serviceability loads, therefore we're going to adopt G 30.54 and Q 5.64. we're not going to adopt these two numbers here. Okay, so what that means is that the overturning moment is going to be 30.54 here times 1.3 plus 5.65 times 1.8. that is 49.87 kilonewtons meters. So m net is 168.29 minus 49.87. we've got that m net is equal to 118.42. Now if we just chuck that in that formula, we've got that x is equal to 0.81. so that's the distance from the V force to the edge of the footing. And then what we actually want here with x is finding the eccentricity. So this eccentricity is the distance from the force to the centroid of the footing. So E is equal to B divided by 2 minus x, and that is equal to 0.39 meters. So moving to the next slide, we're gonna have to ensure that the pressure on the footing remains compressive over the entire footing. The resultant V must act within the middle third of the footing, width. Therefore, E needs to be less than B divided by 6. E is B, which is 2.4, the length of the footing divided by 6. So E is 0.39, which is less than 0.4, therefore okay. Now if that was not smaller than 0.4, it would mean that our pressure distribution under the footing would be different from what we shown in the previous slide, and we possibly would have a negative pressure, or we would have a 0. So I do show that in the exercise number 2 that happens. We have a number greater than 0.4, and it's just a different formula. But if you want to understand how all these formulas come together, you just need to watch my pad footing video, and I will link that in the description below if you want to watch the pad footing, and I'll show you where this formula comes from. So what we're gonna do, we need to find the pressure under the footing, right? That's what we're doing. That's why we're doing all these things. So the pressure under the footing is V divided by B times 1 plus or minus 6E divided by B. So we've got that V that we found before, 147.22 divided by 2.4 times 1 plus minus 6 times 0.39 divided by 2.4. And then we've got P max and P minimum. So P max, we just add that number, and P minimum, we're gonna subtract that number. So we've got that our maximum pressure is 121.16 and the minimum pressure is 1.54 kPa. So that means we've got compression over the entire footing, and we are utilizing the whole footing, which is good. Now what we're gonna do with this number, we're gonna check the soil report or carry out a site inspection and ensure that the allowable bearing capacity of the soil is greater than 121.16 kPa. So if QA is greater than 121.16 kPa, we are good, we are okay, the bearing check capacity passes. Now what we're gonna do, we're gonna calculate the flexural steel reinforcement for the footing, and we treat the footing as a wide cantilever beam with the critical section at the face of the wall. So we've got the critical section here at the face of the wall, and I'm gonna show you the next image here, and we treat this footing as a beam. So what we need to calculate here, we need to calculate this distance here, right? The distance from the face of the wall to the edge of the footing, and that distance is 2.4 meters, which is the whole length of the footing, minus the thickness of the wall, which is, or the width of the wall, which is 0.19. That gives us 2.21 here, and we have that the self-weight of the footing plus self-weight of the soil plus surcharge, right, which is all the vertical loads that we have here, they act at the middle of this rectangle, at the centroid. Okay, so that means 2.21 divided by 2, which is equal to 1.105. Now we want to know the pressure P at the face of the wall, because we don't need to know this portion here. We're just interested to know this sort of triangle here, okay, this trapezium here. How are we gonna find that? We're gonna use similar triangles. 121.16 divided by 2.4 must be equal to P divided by 2.21. And then we're gonna find that P is equal to 111.57 kPa. In reality, this is a trapezium, so you would have to subtract this 1.54 from this number here. But since it's a very small number, we can just assume that this is a triangle and do similar triangles. Now what we're gonna do, we're gonna find the forces that act on this cantilever beam. And how we find these forces? The forces are equal to the area of these figures. Okay, so this force here is the area of the blue rectangle, and these forces here are the area of the trapezium, which is the area of the yellow rectangle plus the area of the green rectangle. So let's just bring that image next here so we know what we're doing. The force of the green rectangle is 1.54 times 2.21, which is this distance here, that's 3.4. So the applied moment is force times distance, so 3.4 times 2.21 divided by 2, because the centroid of this rectangle is just the length divided by 2. That gives us 3.8 kilonewtons meter. Force of the yellow triangle is 111.57 times the height of this triangle, which is the length here of the footing, 2.21, divided by 2. Okay, so area of triangle, base times height divided by 2. So we've got 123.3. And the moment is 123.3 times the height of this triangle divided by 3, because it acts at the middle, it acts at 1/3 of the height from the base, as we discussed before. So that gives us 90.8. Okay, so now let's focus on the blue rectangle. Instead of breaking this down into force and the moment, I'm just gonna do straight calculation of moment here, which is the area of the blue rectangle for the surcharge. Okay, so that's 5 kPa times this distance here times 1 meter length. That's 5.2.5 times 2.21 times 1 times the distance from where the force acts to the fixed end. Okay, so that's 2.21 divided by 2, 1.105. We're going to do the same thing for the moment. We've got WS is 113.94 that we calculated previously times 1.105, and we find the moment, the bending moment for 126. And finally, the self weight of the footing. I called here WB, but it's WF, base moment. So that's the self weight of the footing times the same distance here, which is 1.105. That's equal to 17.6 kilonewtons meter. For a strength check, we're gonna have to factor those loads again. For the bearing check, we use serviceability loads, and now we're gonna use the strength loads. So we're gonna factor these numbers by 1.2 and 1.5. So the surcharge is live loads, 12.21 times 1.5, and the base moment and the soil moment, they are the dead loads, and then we're gonna multiply them by 1.2, and we're gonna subtract that from the yellow and green bending moments, which is 90.8 plus 3.8. That's gonna give us 96.1 kilonewtons meters. Okay, so let me explain what we did here. We found the bending moment from these forces here, we found the bending moment from these forces here, and we subtracted we pretty much subtracted these bending moments like the M net. Okay, that's what we found here to get a resultant bending moment, and we found that resultant bending moment is 96.1. So what we need to do, we need to design this reinforced concrete beam for the bending moment of 96.1 kilonewtons meters. So how we do that? We know that M star is 96.1. We're using a 20 MPa concrete. You can use 25 MPa as well if you want. We're using 50 millimeters cover. We're using N16 bars. B is 1 meter into the page. Remember, it's 1 meter long wall. D is the depth of the footing, the thickness of that footing, which is 300 millimeters. And then we've got the effective depth of the footing, which is 300 minus cover minus half of the bar diameter equals to 242 millimeters. So before we go ahead and calculate the capacity, we're going to calculate the minimum steel reinforcement. So the minimum steel reinforcement given for a beam, a reinforced concrete beam, is this formula here, and it gives us 400 millimeters squared. Okay, so this formula is pretty much 0.2 times d squared divided by little d squared times FCTF divided by FSY times BW times D. We have all these values above here. Okay, the ones we don't have is FSY, which is 500 MPa for steel. FST is 0.6 square roots of the concrete strength. BW is 1000 that we've got here. We have pretty much all the values, so that gives us 400 millimeters square. That's not much steel, so we know that we will have to calculate the steel reinforcement, because surely it's going to be greater than 400 millimeters square. So to calculate the steel reinforcement, we're going to use this formula here. And if you haven't seen this formula, you can watch my YouTube video on how to design a reinforced concrete beam like a ninja. I'll leave the link in the description below as well if you're interested and you wanna watch that video. Just go to the description and you will find the link in there. So AST, which is the area of steel, is the moment M star divided by a factor times FSY times 0.9 times little d. This moment here, just change that into newtons millimeters. The 5 factor 0.85, FSY 500, 0.9 times the effective depth, which is 242. That gives us an area of steel of 1040 millimeters squared. The block wall has N16 at 200 centers. Remember that we calculated that before. We calculated that the reinforcement in the wall that we're gonna use is N16 at 200 centers. So we've got 1 bar in every core of the masonry block. It's a good practice to match these reinforcement in the footing. So what we're gonna do, we're gonna use N16 at 200 centers in the footing as well, which gives us an area of steel of 1005 millimeters square, which is slightly smaller than 1040 millimeters square. However, due to approximations I have used throughout my calculations, I'm confident that N16 at 200 will cut it. And we're gonna double check this right now, okay? So we're gonna confirm that an estimate above is correct. Let's make sure that this N16 at 200 centers will work. So what we're gonna do, if you watch my video of reinforced concrete beam design, you're gonna see that we need to calculate this little a here, which is the depth of the rectangular stress block. So these formulas are from your reinforced concrete classes at uni. If you remember that you've got the rectangular stress block, and you can find these formulas. These formulas are derived from that rectangular. So we pretty much find the depth of the rectangular stress block, which is 30.64. Alpha 2 is equal to 0.82, and you can find that in AS 3600 clause 8.1.3.1. Little c is the neutral axis depth, which is equal to A divided by this letter here. 30.64 divided by 0.92 equals to 33.3 millimeters. This letter here that I forgot the name is equal to 0.92, and you can find this from this clause here. So both of these numbers have been updated from AS 3600 2009. So if you're using the previous standard, you might find you will get different numbers for these values, okay? So make sure you're using the current Australian standard, AS 3600 2018. Now KUO, which is the neutral axis parameter, is equal to C divided by D. That's equal to 33.3 divided by 242. That's 0.14, and that must be less than 0.36, which is less than 0.36. Therefore, we are okay. We're good to go. Now we're gonna do the final moment check, okay? So the final moment check is given by phi times ASC times AFSY times FSY times D minus A divided by 2. So we've got the phi 0.85 times area of steel that we had it before, N16 at 200. Oh, there we go, it's here. Times the yield strength of the steel times the effective depth minus the depth of the rectangular stress block A divided by 2. And then we have that phi MUO is 96.8 kilonewtons meters, which is greater than 96.1 kilonewtons meter. That means our footing can resist the loads in bending. Moving to the last slide, we're going to see how we can detail this retaining wall. Okay, as previously seen, we have 1 meter high of 300 series, and then we have 2 meters high of 200 series. We're gonna lap the N16 at 200, 700 millimeters with the N12 at 400. That you probably calculated that by yourself just to make sure that works, right? I know it works, but just do a quick calculation yourself for training purposes. And what else? The starter bars here, we just matched with the reinforcement of the wall. So we've got starter bars which are N16 at 200 as well. They're cogged into the footing here. The main longitudinal, the main transversal reinforcement for the footing is N16 at 200 that we just calculated, right? We calculated the footing to resist bending. What else? We do have some horizontal reinforcements here, okay? So horizontal reinforcing is necessary to control cracks from temperature change and shrinkage. So we do need to have reinforcement here horizontally, right? So that's into the page. We're doing N16 at 300 centers, and in the wall we're doing N12 at 400 centers horizontal. So that's the reinforcement here that goes into the page. I do cover these calculations in the ebook. So pretty much for this video, what you need to know is that these reinforcements, they're there to control cracks from temperature change and shrinkage. Another tip here, all reinforcement placed on the tension face of the element. Okay, so you can see that all the reinforcement here is placed where we're gonna have tension on the structural element. So if we have forces trying to push this wall here, the wall is gonna try to bend this way here, right? Let's just get a pen. So the wall is going to try to bend like this. So that means we have tension on the left hand side. That's why we've got the steel reinforcement placed on the left hand side here. Footing, same thing. We've got all that soil, all that load trying to push the footing down, and you have the footing fixed to the wall as a cantilever beam like we designed, remember? So that means this soil is pushing the wall, so pushing the footing, so the footing is trying to do this, right? The footing here, that's a terrible draw. That's a terrible drawing, I know, but anyway, so the footing is trying to do this, look. So we've got tension on the top face. Anyway, we have tension on the top face, that's why we have reinforcement at the top here of the footing. Another tip here, even though not necessary in this example, structural engineering offices will add a key to the footing of standard retaining walls to account for lack of information about the soil. We will see the need of a key in the next exercise. So in the next exercise, when we calculate in the ebook, in the next exercise of the ebook, when we calculate the sliding, we're gonna notice that we will need a key to prevent the wall from sliding. And what this key is just a continuation of this footing here, right? So we've got a key here. So the footing, everything's poured together, like all the concrete's poured together here. But what happens is this key here will prevent, we've got soil here, This key will prevent the wall from sliding. And what I'm saying here is that a lot of at least all the engineering offices that I know, they will install a key even for this type of wall, even though it might not be necessary. There are a lot of factors that we don't account for, and soil is always really hard to quantify the parameters. That's why we are going to use a key for a real life project. What else? A check of the out of plane shear in the wall and one-way shear in the footing shows that the wall and footing have adequate capacity without the need for leaks. An example of these calculations will be demonstrated in the basement wall exercise number 3. So in exercise number 3, what I did was I checked the out of plane shear capacity of the wall. Okay, because always when you're checking a structural element, you don't only check the bending moment, you also have shear. So in the exercise number 3, you also should check for this example. If you're doing a real life exercise, you need to check for the out of plane shear of this wall and also a one-way shear of this footing. That was pretty much it, guys. I hope you learned something in this video, and I hope you enjoyed the explanation, and I'll see you next time. Thanks for watching.